Thank you, Mr. Chairman. Good morning, ladies and gentlemen. It's for me a pleasure to talk here. And I would like to introduce FRT with high current injection. Okay, I will start with motivation. Then I would like to talk about future requirements coming up. I will introduce test results for symmetrical and asymmetrical failures, and I will give a summary. Motivation is dynamic voltage control is one of the pillars of ancillary services. It is an autonomous function that means that it is activated regarding the measurement at terminals of the power electronic device of the inverter, and it is it is a function that has a more local influence, and a lot of aggregated devices acting as FRT devices may have a global impact in case the voltage dip is caused in the transmission grid. Future requirements. Up to now, mainly the requirements require 100% the nominal current during voltage dip. But there are coming up new requirements, for example, in Dubai, require 120% of nominal current during a voltage dip. And that's not all. They are requiring 50% of this 120% within 20 milliseconds injected, and the full range of additional reactive power has to provide within 60 milliseconds. So critical factors are the amplitude, the 120%, and the dynamic requirements. Here you see a typical curve of FRT current during during a voltage dip. And what you can see is you have a response time in that case 14 milliseconds. And then you have something like an overshoot because the control cannot react fast enough. And then you have an oscillation until the final FRT current is reached. And in that case, the settling time is required to 60 milliseconds, so it has to be tuned in a way that we are sure to reach the 120% within 60 milliseconds, and therefore we have to increase the set point from 120 to 126% to be sure to reach the 120% after 60 milliseconds. Why FRT current above 100% of nominal current? What could be reasons for? One reason is voltage support effect is proportional to the current flowing during FRT. Thus, the FRT current of 120 to 130% of nominal current stabilized the voltage better than 100%, it's clear. Then you have more flexibility in engineering of protection devices in the grid in case you have enough current in case of a failure. Then you have extra reserve for starting large motors in weak grids, or in case you switch on fact devices in the grid. The high FRT current is the premise in case you install batteries in relative small grids, or in case the grids are dominated by batteries. In that case, the so-called inertia has to be provided by the grid, and when you have a voltage dip, the grid has to, or the inverter has to react with a high forthright through current. So higher forthright through currents expands the degree of freedom while installing large solar and battery equipment. What are test results? First, I would like to introduce our test equipment. We have seen in the last presentation a test equipment on medium voltage side with so-called test containers. With such an equipment, you can perform the test mainly at site, and you have to accept the conditions at site. So in case you have not nominal ambient temperature, or you have not nominal power before the event, you may test the device not under worst case conditions. Thus, we build our test equipment. We have a voltage source inverter to generate the voltage dip, and the device under test is a current source inverter and reacting on the voltage dip. And what you see here is you have to cover the losses of this test setup from a DC source. And the losses are not very high in percentage, but they are there. And here you can see, in case you have no DC source available, forthright through current cannot be injected until zero voltage, because you need some active current to cover the losses of the equipment in case of a forthright through event. And when you have STATCOM devices, they can react as forthright through sources in most of the cases, but not in case the voltage dip is too deep. And what we can tune here in our test facility too is we can rise the voltage, the DC voltage, during forthright through until nominal DC voltage. That stresses, of course, the equipment more, as it is only below nominal voltage. What you should consider is, in case you have a voltage dip and you inject reactive power during the voltage dip, the voltage in the PV array will rise to no load voltage, because there is no burden left for the array, because the inverter is injecting only reactive power, not active power. And in that case, the voltage in the equipment in the array rises. And that can be tested very efficiently in such a test lab. So you can tune the devices to nominal or to worst case conditions. What we did. Okay, what are results? In the upper part of the figure, you see the voltage dip. You have nominal voltage, then you have the voltage dip, and after that you have nominal voltage again. In the middle part, you see the reacting current. We have nominal current, then you see the overshoot in current during the start of the event. And then the current is controlled to 120% or 130 in that case, the nominal current. And after the event, you have ramped up the current in the way the standards foresee it. And the lower part of the figure, you see the RMS values of the current. You see in blue the reactive current, in red the active current, and green the apparent current. So during the event, the reactive current falls to nearly zero or to zero. The reactive current rises and falls again after the event. I would like to talk about dependency of FRT functionality in transformer configuration. In case you have multi-windings transformer and every inverter has its own low voltage winding, then prospective circulation currents between the inverter during the event are blocked. When you have multi-inverters connected to one low voltage winding of a transformer, circulation currents may occur because the arrays are not galvanic coupled directly, but they are strongly coupled via the parasitic capacitors of the modules regarding ground. And thus, circulation currents with switching frequency of the inverter may occur. And that is, may cause critical states. And when a single inverter stay alive during fault right through, it mustn't be the case for a couple of inverter connected to the same low voltage winding of a transformer. Thus, in case of multiple inverter connected to one low voltage windings, fault right through tests should be performed for the entire setup with real PV generators. Test with one inverter only is not sufficient from our point of view. And I will show the result for asymmetrical failures. To be honest, in most of the cases, the failures are unsymmetrical because normally only one or two phases are affected from a failure, not all three phases. And here you see the voltage dip. We have, in that case, phase to neutral voltage of two phases are the same. That means we have a short circuit between the phases, and the third phase is not affected. Then you see the reaction of the current. Again, the current is injected. We have somewhat overshoot at the beginning of the event, and then at the end of the event, the current is rising with the gradient foreseen in the standard. And what is important is that the positive sequence voltage determines positive sequence current via key factor. When you inject, for example, reactive current during the event in the not affected phase, then you rise the voltage in the not affected phase beyond the nominal voltage, and that may harm loads connected to that phase. Okay, the summary. An FRT current of 120 to 130, the nominal current, is feasible for standard inverters. Test results for the symmetrical and asymmetrical voltage dips have been presented here. Fault right through tests should be performed with no load voltage on DC side and not with MPP voltage. under controlled test conditions. If the grid voltage dip falls below a certain limit, fault right through is feasible only in case a DC power source is available, for example, a PV generator or battery. VAR compensation units cannot contribute in such a case, or not in the full range. In case of multiple inverters connected to one low voltage winding, fault right through test should be performed for the entire setup at real PV generator or multiple voltage sources with large ground capacitors. Test with one inverter is not sufficient. My company has an holistic test approach for the FRT functionality and a lot of experiences to develop the devices in appropriate way. Thank you for listening. I would be happy when you have any questions.
Any questions? 2, 3 questions?
Now you have to do this for grid tie inverters, all the 3 types, like string inverter, central inverter, all those things have to be done, or string inverter you have shown?
No, that the test results I've shown are for central inverters. But for string inverters, tests can be performed, of course, in the same way. But for string inverters, in the moment, it's not possible with 120%. That's not foreseen. But for central inverters, it is. Mm-hmm.
Yeah. Just one more question from my end before you move on, please. So to follow up on the last question, individual inverters, like in domestic world, can they be engineered to give similar capability, or is this only for large solar parks?
Yeah, it is possible to engineer them in the way. Hadn't been done up to now. But when the standards are regarding, then it is possible. From the semiconductors point of view, there should be enough reserve in most of the cases to do so. In case the dip is not too long, in case it is 300 milliseconds somewhat, then it is feasible. For seconds, it's not that easy.
Rajshekhar, now CEA in India is coming up with standards for FRT.
Yes.
But when you say that if there are more than one inverter, you need to be looking at it as a system. So from your perspective, from the policy and regulatory, from the guidelines for the large utility scale power plants that are coming in India in solar, what is your suggestion as to how it should be implemented and how should it be tested?
Yeah, it should be tested in a way that the real conditions are. Yeah, what I said, when you have a system, galvanic isolated system, then you can separate it relatively easy during the test. When you have a galvanic coupled system and you have, especially in the PV generator, because you have that large ground capacitors, then you have to test under conditions rebuilding the system, let's say, or minimum in a type test. It is not realistic to test it at every site. That is not economic. You have to specify a type test that considers the circumstances you have at site. That is very important. If you do not so, maybe you have the effect that FRT is working in lab, and is do not working in the field, and that is a pity because your grid is not supported.
So are you saying that we should test it here? Are you saying you should test it always in the field?
No. You should test it under circumstances in the field, yes, but better in a lab, rebuilding the field, because in the field you may have no sunshine at the day of test, or little sunshine only. You may have low temperatures or high temperatures, and you have to have to test under all conditions in a way. And that therefore it is important to rebuild the test in the lab, from my point of view.
But you did talk about testing it on the field in your presentation.
In my presentation, not. In the moment, it is standard to test in the field. That is better than nothing, and but as more penetration you have, and as wider the conditions are, as more important it is to test under all circumstances can occur.
Thank you. Raj, one more question.
Hi, I'm Pavitra representing DNVGL. So does your inverter compensate the harmonics effect as well?
The harmonics? Okay, it's a totally other subject. What the inverter do in the moment is they have a harmonic current control for low number of harmonics, so between second and seventh. Above that, the inverter has, or the circumstance has to be designed in a way that the harmonics not occur, but second, fourth, fifth, and seventh harmonics can be compensated by the inverter, yes, and they are compensated. Yeah.
Thank you.